Okay, thanks, Gary. So I was kind of chuckling over here when Gary described the initial vendor interaction for the Crossroads machines because, yes, that was us in the meeting saying, well, what do you want? And them telling us, well, what can we have? Us asking, what do you want? Them telling us, well, what can you give us? I think we finally have learned how to interact with them by going off and trying to figure out what we can give them. And a big reason for that is the document that Dave and Gary put together, which has been a big help for us. And we hope we see more of that as we go forward. Just very briefly, I manage the High Performance System Software Group at IBM TJ Watson Research Center. Our group is part of the Data-Centric Systems Department, and that's led by Jim Sexton. We have, in the past, built the Blue Gene line of supercomputers with IBM systems, and now we're working on delivering the IBM Coral systems, Sierra and Summit, for Livermore and for Oak Ridge. And of course, we want to design systems for, we want to design the Crossroads and perhaps deliver that as well, and we're looking forward to exascale. So in my talk, I'll just briefly outline what we see as the biggest challenges going forward. Of course, we believe that burst buffer will help us to meet those challenges. And we're finding that having more information in the form of the Apex Workflows document is also helping a tremendous amount. I'll give you a flavor of the analysis that we're actually doing. It's fairly simple modeling, but it has given us some very nice insights into our design. And we are incorporating it into our design process. Also just a few stories from our interactions with the labs. Then I'll just briefly describe the Coral burst buffer design and how we think that will change or not change as we move forward depending on our analysis and our continued interactions with the labs. All right, so the challenges that we face. The biggest challenge that we face is that current parallel file systems cannot provide an adequate fraction of the aggregate disk bandwidth. Okay. If this were not the case, our lives as vendors and customers would be quite simple because we would just add, well, the customer would tell us how much they need, and we would just write the bill or write the bid for that. Now, why can't we do this? Well, the HPC workloads that we're facing, and this is well documented in papers by guys like Gary, are quite a mixed bag. And they're quite a mixed bag for a couple of reasons. One reason is one reason is what they do. For example, you could have a checkpointing scheme in which you write to end files independently, but this is not the most usable scheme. So it's quite common that applications have multiple processes writing to the same file. And this is a performance issue because file systems tend to be pretty lock-happy, and this degrades performance. Another issue is that what we actually see in terms of utilization. We have very bursty traffic in the form of checkpointing, but then we have a lot of underutilization. In a study that Gary did on Intrepid, which is a Blue Gene P machine, 1/3 of the bandwidth, if I remember correctly, was being used 99% of the time. Okay, the maximum throughput on that machine, the maximum throughput that they measured on the machine was something like 35 gigabytes per second, but the average was only 2 gigabytes per second. So there's a big gap between full utilization and the average utilization. Okay, so another challenge that we're facing is the exascale applications. We've been told that we could face or we could see application checkpoints on the order of 32 petabytes. Okay, so if we want to transfer that from main memory, out of main memory, into a burst buffer onto disk in say 30 minutes, we need bandwidth on the order of 16 terabytes per second. Okay, so the Trinity machines, which will be the latest supercomputer that I think comes out this year, the bandwidth to their parallel file system is on the order of 1.5 terabytes per second. Okay, so we're a long ways from that. Okay. All right, so burst buffers will certainly help us. As our keynote speaker explained to us, disks give us a lot of capacity, which is great, but they don't give us the latency or the performance. So burst buffer fills the niche between, or gives us the latency, but it doesn't give us the capacity, but it fills in the memory hierarchy pyramid very nicely for us, or at least we think it can fill the memory hierarchy very nicely for us. So we really see burst buffer as being integral. Trinity will have burst buffer, and the Coral systems will have burst buffer as well. As I'll explain a little bit later, the architectures are very different, and going forward, weighing the pros and cons of the different architectures is going to be important as we finally settle on what the architecture should be for Crossroads and for exascale. All right, so something else that has been really valuable to us has been the Apex Workflows document. It's been a goldmine of information for us. And here I've outlined some of the more important characteristics that the document has given us. Workflow phases, campaign duration, workload percentage, wall time, resource allocation. And this is very important to us, the anticipated increase factors by 2020. One of the big questions to us is how will the applications and workflows scale to the machines that we're actually delivering. I/O details and the amount of data retained, of course, for capacity reasons. This has been great, and our initial reaction was to put together some modeling for this. And what we did was we put together a spreadsheet, and we have a Python version as well, which allows us to sort of scan through the parameter space very quickly. And we've been actually presenting our results to the Apex labs in, I don't want to say weekly, maybe bi-weekly meetings, once a month meetings. They haven't been completely regular, but when we have results, we try to show them to the labs. All right, so I'll try to give you a flavor of what we're actually doing. Here we have specifications for 3 machines, Cielo, Edison, and Trinity. Of course, Trinity is the only machine here that actually has burst buffer. The burst buffer architecture for Trinity is sort of a, I don't want to say centralized, but 8 compute nodes share 1 burst buffer node. So the burst buffer nodes are the orange there, and the compute nodes are the green. Okay, now this is different from the Coral burst buffer architecture, in which we actually put the burst buffer on each of the compute nodes. Okay? So what are some of the results that we've been generating? Okay. These 2 graphs show the checkpoint overhead that we've calculated versus the checkpoint interval for 2 of the workflows. One is LANL LAP. I think that's Lagrangian Application Project. Okay. And the other is LANL Silverton, which is a computational fluid dynamics workflows. On the left here, and you can see that the dotted line is, I didn't label that. That's actually the Daly Young checkpoint interval, okay, which is the optimal interval that we can calculate. And of course, we went below that and we went above that to see what the behavior is. The left graph shows the LAP performance with just Trinity parallel file system, which is that top blue line that you see. And then we have 2 lines for the burst buffer. One is the purple line, which shows what happens if we're able to get full bandwidth to the burst buffer from the checkpointing. And the other is if we're only able to get half of the bandwidth. Okay, so looking at the dotted line, we can see that the Trinity parallel file system, the checkpoint overhead with that is on the order of 18%. Okay, which is pretty high. However, with the burst buffer, and if we're able to get the full bandwidth, it drops below 10%, which is definitely much better. But we do have questions about whether or not the contention at the burst buffer nodes will allow us to get that. So that's why we wanted to show the range of possibilities there. Okay. So you can see if we only get half of the burst buffer bandwidth, we actually move much closer to the Trinity parallel file system. We suspect that this is something that we'll have to verify once the Trinity machines come out. It's pretty difficult to model at our level what's actually happening. Okay, so on the right-hand side, we have Silverton. And here we just compared Cielo to Trinity. Cielo is the red line, and Trinity is the blue line. Cielo doesn't do that well because, well, it doesn't have any burst buffer. Trinity comes in at about 20%, well, a little less than 20% overhead for the checkpointing overhead. And this represents about a 20 times improvement over the Cielo parallel file system, which is great. Okay. All right, so these two graphs give a little bit more detail about what's actually happening, and it shows some other dimensions in which that we're actually modeling. It's a little difficult to read, but I should have made the legends a little bigger. But the gray boxes, the gray rectangles represents the computation, and the green boxes represent, the green rectangles represent the I/O. Okay, in each of the graphs, the left represents Cielo and the right represents Trinity. Okay, and on the left-hand side, we have hours and percentage, just different ways of showing the same data. For LAP, and on the right we have the same format for Silverton. As you can see, the Trinity burst buffer helps tremendously. You know, the green boxes go down really small, or they're made kind of tiny, which is great. Now the gray boxes are not as small, and this is something that we're trying to model as well, because we also want to understand total runtime too, and how the workflows are affected by the different architectures. And what we've done with this is that for these particular graphs, we're assuming a speed up from Cielo to Trinity of about 40x. And this includes the Intel Phi that's been promised with the Trinity machines. Now, we don't see a 40x improvement, and that's because we're assuming a memory-bound application of memory-bound about 2/3 of the time. And memory bandwidth is not speeding up that much. We believe that the memory speed up will be about 1.25x. Okay, and that's the effect that we see here with the computation not being sped up as fast as what we see with the processors. Okay, that's something that we're actually trying to look into more detail, and we're actually doing things like pulling DIMMs out of machines to play around with different memory bandwidths to find out what applications actually do with different memory bandwidths. Okay, so the Coral burst buffer. We took a different, as I mentioned before, we took a different design point for Coral. We decided to go ahead and put a burst buffer on every compute node. And we did this because we wanted to get maximum bandwidth to the burst buffer. And that's an easy way to get maximum bandwidth. Now, of course, this has pros and cons. With the Coral burst buffer architecture, we are, of course, the checkpoints that you store on the Coral burst buffer are going to be exposed to the compute node failures. And there are a couple possible cases. You know, one case is that you have a transient software failure, okay, and the burst buffer is not affected at all. And another case as well, the node goes completely down, requires human intervention, which doesn't come until 3 days later. So you have to actually rebuild from or start start your computation again from a checkpoint on the parallel file system. Okay. Now, with the Trinity burst buffer architecture, you have a similar problem, but at a different granularity, of course, because you have 8 compute nodes sharing a burst buffer node. At least this is what we think is happening. If a compute node goes down, of course, the burst buffer is not affected. But if the burst buffer goes down, well, many checkpoints are affected. And what we're trying to do is we're trying to model this behavior to try to determine before we actually bid for Crossroads and for Exascale, you know, to get a better idea of what the pros and cons will actually be there. Okay, and we're definitely looking forward to seeing some studies from Trinity to try to refine our model as well. Okay. All right. So ongoing work. Well. We continue to try to refine our model. I mentioned refining the memory behavior. That's one aspect. We're also trying to refine the processing behavior. As you probably know, the Coral systems have GPUs, CPUs and GPUs. So we're trying to understand how that affects the behavior of the systems as well. We're also trying to model the network at a much finer granularity as well. We're just assuming raw bandwidth, but it would be nice if we could also model contention at some point as well. We're also trying to, as I mentioned before, understand the differences in the architectures. One thing that I didn't mention before is the cost aspect. And this was actually brought up by the labs in our discussions, not by us, and certainly an example of benefit of the interactions that we've had with them. They pointed out that if we go with a burst buffer per node, it doesn't give them a great deal of flexibility in terms of pricing. Because if you have an aggregate burst buffer node, you're able to sort of amortize the costs of different types of different sizes of SSDs that you put into the burst buffer node. You don't have those same sort of price points if you go with a single burst buffer per compute node. Okay, so we thought that was an interesting point, and that's something that we're trying to take into consideration in our modeling as well. It's difficult because you have to, of course, project out costs many years from now, but you know we'll make an attempt at it and see what we come up with. Okay, so I was, as I said, I was chuckling when Gary was describing the initial interactions with the labs. You know, we really wanted to know what they wanted, but they kept telling us, well, tell us what we want, you know, tell us what you can do. So I think we've come to that, and a large part of that is due to the workflows document, and we hope we see more of these types of documents. I was talking to Ian Connor, who will be talking a little bit later from Cicero. He's with, and they're focused on the SKA project, and he was mentioning that they're looking at something similar for the SKA workflows, and we think that would be fantastic as well. So that's all I have, and thank you for listening.